Now it's
Okay,
good.
thank you, and sorry for any inconvenience to all the participants. Okay, thanks for the introduction, and I'm very thankful to the School of Software, Northwest Polytechnical University, Xi'an, China, for inviting me for this talk. And this is really a great opportunity for the students and the researchers to be in contact with the researchers throughout the world and to extend the collaboration by having their knowledge on different issues of real world. Okay, so this talk is all about explanation, intelligent, artificial intelligence. So uh, since long, artificial intelligence is well accepted, and the people are following the artificial intelligence algorithms and approaches for getting the real-time decisions. So what's the issue that this extension, what's the reason that this extension of artificial intelligence is needed? So there could be a reason while working on the issues faced by the people and the researchers that the people are curious why this decision is, what's the purpose of the decision, how we can get the reasoning behind this decision. So due to these reasons, artificial intelligence approach is giving us a model, giving us a scenario that is like a black box. We have the decision, but what's the reason behind it? We don't know. We have the opportunities, but we don't know what's the reason behind it. So to come up with a solution to grab this solution, we have this artificial intelligence extension that is known as explainable artificial intelligence. So this talk is majorly comprising of two major components. One is uh, one is covering the reasoning and the opportunities and the scenarios of this explainable AI, and the second one is its case study from where we can understand that why there is a need of explainable artificial intelligence is. So this explainable AI, as we presented a while ago, this AI is uh, like a black box, and we have a lot of algorithms, but the outcomes of this algorithm is like a black box. So the rationale behind the output of an algorithm is not understandable by the humans. So there is explainable artificial intelligence, and this explainable artificial intelligence is we can say it a white box, means that we can look inside and we can have the idea that what's the reason behind it. And for those we have the special implementation of artificial and the machine learning algorithms like DT, decision tree, the Bayesian networks, the sparse linear models, and many others one. So the researchers are looking for the ways to make this black box model more explainable by, for instance, by incorporating knowledge graphs and other graph related techniques. So if we define concisely what is explainable AI, then we can say that this is a set of processes and methods that allow human users to comprehend and to trust the results. Means that a well comprehension, trustworthy results, where the user can blindly follow why I am accepting the decisions, and the output created by machine learning algorithms. So here is a very beautiful depiction of why this today's artificial intelligence is different from the explainable artificial intelligence. So this traditional artificial intelligence, there is a training data and machine learning process. It is passed by the machine learning, and based on this outcome, this we have the learn functions, and from the learn functions we have the decisions. Means the data and input to the system, the system is trained, and based on the training we have the decisions, and we have the learn functions, and based on the functions we have decisions. But we have many curiosities, many questions why this out, we don't else, why only this, and what to do, and how do I correct an error? If there is some error, then how do I correct it? Another one is that is passed through the new machine learning process, and that is the outcome is fed into the system that is particularly comes under the umbrella of explainer models. And based on those models, we develop the interface which come up with the reasoning of why this decision is there. So based on this explainable AI, we can answer what was the curiosity before that, and that answers could be yes. I understand why this decision is selected. I understand why not the other decision is not selected, and what the way to succeed, what the way not to succeed, and why I trust, and where are the errors could be that can be rectified for a better decision making. Uh, this explainable AI, we have the major four principles based on which this explainable AI works, and this constitutes explainable AI, that is XAI. And these four principles are defined by the National Institute of Standards, the US Department of Commerce. And what are those four principles? And the one is the explanation, the meaningfulness, explanation accuracy, and the knowledge limit. If we combine all those four principles in one statement, we can say that the output must be accurate and understandable and explainable, means that it has some evidences. And if the parameters are not fulfilled, and if the required circumstances are not available, then there should be no decision. Means that with the confidence value should be high. So this explainable AI is based on four principles, means that the output must be with the strong evidences, with there is some reasoning, and that reasoning is understandable, and that reasoning is accurate, and it is presented with full confidence. So must be some sufficient confidence. Okay, here is the output with accurate and understandable reasoning with high confidence. Okay, as the topic of the title of this talk is the core idea, the output, and what are the impact and contribution is explainable artificial intelligence. So just by giving the theoretical aspects of all those definitions, let's come up and jump into the environment, into the circumstance, and by giving a case study. That is the explainable artificial intelligence approach in combating real-time surveillance of COVID-19 pandemic from CT scan images and X-ray images using ensemble model. Here in this topic, in this case study, we have the data set in the form of the CT scans, in the form of the CT scan. The CT scan, yes, means computerized tomography and the X-ray images. This computerized tomography scans is far better than the X-rays images because these CT scan means computerized tomography. We also use the X-rays, but from different aspects, and combines from different angles around the body, and uses computer processing to create cross-sectional images. That is mean the slices of the bones, the blood vessels, the soft tissues inside your body, and the CT scan study images. It provides more detailed information than we do with the plain X-ray images. And these images, the CT scan images and CT scan and the X-ray images are of the potential COVID-19 patients. Those could be the true patients or the false patients. Means that patient or the healthy person. And this technique of explainable AI, we are implementing on these data sets by using the ensemble model. There are many models like we have many models in that are trained with ImageNet that is comprising of 1,000 of images. So we have this motivation behind all this scenario. Means that when the doctor have the reports of the patients, it's most of the cases based on these two CT scan and X-rays. Most of the cases, it's not very easy to detect the severity of this problem, and based on the current literary work, we have less severe and non-severe instances of COVID-19 as compared to the severe cases, and this is really good news. And if we have the data that is comprising of high dimensions, means that the too many columns, too many fields are there. The traditional algorithms can't be used. So for that, we use the convolutional neural network, CNN. And this training process for these networks is more complicated, more time consuming, the resource intensive. That's why it's not, that's why with the traditional methods of convolutional neural network, we can't use those for the scenarios where the environment, or where we have the IoT-based treatment modalities. There are the resource constraints from the perspective of energy as well. So we have specialized models for those, that is MobileNet as well, and that is the computational neural network aspect. So what the proposed mechanism we have, in our proposed mechanism, we are combining this deep learning and machine learning classification algorithms. And the CNN model, what the CNN model we have designed, and we did many experimentations with by checking the accuracy of the results, and with various parameters, and we concluded that this number of 350 features uh, are in best form, are in a good number of results. Later on, I will show various experimentation results that will represent, that reflect that why we selected only these 350 important features. Another important thing in our mechanism, in our solution, is the voting-based ensemble model. So the first one is, what is ensemble model? Means that we have we are not following just a single algorithm or a single model. We are having multiple models. We have multiple algorithms, and those multiple are based on the results obtained from those multiple algorithms. We are coming up with a final result with that output, with that outcome that has the maximum value, that has a maximum points. So means that this ensemble model is synergistic mating, means that the strength, the power of multiple models, multiple algorithms. And this is this leads to the terminology of voting based ensemble model. And in that ensemble model, we have the Gaussian Naive Bayes, this SVM, sport vector machine, decision tree, logistic regression, random forest, and all these. And by checking the performance of our proposed method, that whether we are getting what we want to get out of this experiment, out of this mechanism, we implemented the Grad-CAM, and that is the gradient weighted class activation mapping. Let me tell a brief about this Grad-CAM. This Grad-CAM is a class discriminative localization technique that is for making any convolutional neural network model that is more transparent by producing visual explanations. And in this in the experimentation, and we represent this visualization in the form of heat maps, and the cumulative cumulative heat maps, and the heat maps as well. And also we implemented the distributed stochastic neighbor embedding. This neighbor embedding is this t-SNE is a unsupervised machine learning algorithm, and that is around 2008, and that is used for exploring high dimensional data. It maps multi-dimensional data to 2 or more dimensions that is suitable for the human observations. And this proposed method is evaluated, is implemented and evaluated with the 2 data sets containing 1,646 and 2,485 chest X-rays and CT scans. This proposed approach beats the existing one, as we concluded based on our experimentation with a score of 98.5%. This is accuracy, 99% precision, and the recall value was 99%. Here is the graphical representation of how this overall system architecture of the proposed interpretable COVID-19 detection system that is based on the real-time IoT system. Okay, and here the diagnostic system, the diagnostics of the results, and it's collected by the devices, and then it is saved in the cloud, and this design system is implemented. This designed model is implemented in that system. And what did we use? We use, you can see here in the picture, the 2 layers of the picture. The first one, the 2 rows of the picture, the first one, and this is the second one. And this is the actual, but we implemented a CLAHE, that is the contrast limited adaptive histogram equalization, to improve this low contrast medical images. So now we have a good quality images, and this is image enhancement. And these images are processed and then fed into the neural network system. And here in this neural network system, we have this multiple layer, this convolutional block 1, 2, 3, and 4. By implementing these 4 convolutional blocks, we came up with a dense layer, and ultimately these 350 features were extracted, and we then this is fed into the ensemble system, and this ensemble system is comprising of multiple machine learning algorithms, and each of the algorithms implemented on it and came up with a value of particular features, particular area. This is called the soft voting, and based on that value, we came up with the outcome that whether this image is of the person infected with COVID or not infected with COVID. This is the implementation style, the same as presented a while ago while presenting about the picture, the model, the architecture. In the previous 2 slides, we have iterated around 100 times to correctly classify the images, and we used Python's TensorFlow 1.9 to build the CNN network. And firstly, we used this splitting method, random splitting method, to divide this whole data set. We used random splitting method to divide this whole data sets into the into training data part, and the learned part or the test part, as the tradition, the 80% for the training and 20% for the testing purpose. Here, as we presented a while ago, just before optimum feature selection, we came up with 50, 100, 150 up to 500, and concluded that the optimum number of features are 350. And we have this all we came up with the implementation of these as described a while ago. Here, this summary the same. The most prominent features are selected just in this previous slide. And next, these extracted features are classified based on the machine learning classifiers and the learning ensemble. Then this is interpreted based on the t-SNE and the other one model, and that we call it Grad-CAM. And these are the formula, the well-known, nothing to explain, the self-descriptive, the true positive, the false positive, true negative, false negative, and this all we came up. This is the classification measure with different data sets. Here are the results came up with the implementation of our proposed mechanism. And we have this big number of parameters. And here we have the 27 layers. And after implementing this model, we applied this soft voting method with these classifiers, and we have these values. And the same experimentation we did with other models, that is Inception V3. This Inception V3 is a well-known extension of convolutional neural network. That is the pre-trained means that it is this model is well suited and well tested for the ImageNet that has millions of images and presented with the fine results. So the same experiment as we did with our proposed mechanism, with the proposed model, we did with this Inception V3, and with the VGG16 that is having here the 19, but actually this VG16 is for the 16 layer. This is also pre-trained. This is RASNet, and this is also pre-trained and well-known, and also implemented on successfully implemented and tested with the ImageNet, and it has 175 layers. And this mobile net, as briefly shared before, this is the mobile net, means that the CNN, convolutional neural network, and its many extensions can't be used for the mobile, for the cell phone, for the resource constraint environment, that is particularly for the IoT environment. So this model of CNN, this extension of CNN, the mobile net, is designed, that is also well tested and accepted with these high number of parameters and with these 87 layers. And this gives good results in resource constraints devices. And the same scenario we taken up and implemented this mobile net on it. This is DenseNet 201 pre-tested, and this has 707 layers, and we have this these results. Okay, so if we compare these results, this proposed method, we have the later on the implementation of among the classifiers KNN, we have this value of 0.972 with this proposed method, and with this inception we have the highest 0.84, and we with this VGG16 we have RF, the random forest 0.85, and the same random forest after the implementation of ResNet we have 0.851, and with MobileNet the same random forest we have the value 0.85 and 0.85. It means that as the results reflects, we have the best results with our proposed model with a KNN with the value, with the accuracy value of 0.972, and with F1 score of 0.97, the same value with precision, and the same with recall. And the prediction time it taken up is 0.077. And if we compare it with the other one, the prediction time, with this proposed method, we have 0.07, with this 0.01, with this 0.01, 0.01. Yes, our proposed mechanism is taking the high prediction time, but with the good accuracy. And this time is not much, but anyway, there is a time difference, this prediction time. If we look into this, the comparison of the proposed method with state-of-the-art methods using this testing accuracy with these models, DenseNet, Inception, MobileNet, ResNet, and VGG16, and those have the varied layers, varied number of layers. We have this testing accuracy, and we have epochs, and these 40 epochs means that the repetition of a whole scenario the 40 times, and in this outcome the testing accuracy of the proposed method is outperforming. And with this testing loss, we have the least one with this proposed method, and the previously was the testing accuracy, and this time we have the training accuracy with varied values. This proposed method, the training accuracy is the highest with the proposed method, and with this ResNet, we have the least accuracy in the training, and with this training loss, the highest accuracy the training loss with the highest accuracy is the proposed method, and the least accuracy means that the highest loss is with the DenseNet. We also compared our proposed mechanism with the previously published work, and this research work is published in a well-known from the well-known platforms. They have their different models, just like the first one, this DanceNet and voting-based approach, this deep CNNs. These are different models for on different times for different number of different number of layers and for different target images. But most of these models are well tested and accepted with the ImageNet, and that is previously said comprising of millions of images. And if we come up with if we come to the proposed work, this is having the ensemble method, its precision and recall, F1 measure, and accuracy is compared with the previously published work. And we can conclude from this tabular representation of the results that this work, this proposed mechanism with the ensemble method is presenting overall the far better results as compared to the existing ones. Yes, not in every aspect, but if we comprehend this, we have this better results. Means that the outcome, the understanding of the outcome is better with the proposed method. This is
I'm sorry, you have 2 minutes left. Please.
Yeah, thank you. I'm also winding it up. Thank you for the reminder. And this performance validation with the Explainable AI, we implemented the same one, the gradient class activation map, and the other one, t-SNE. So this is better understandable for the medical analyst and for the medical professionals, and those can clearly where the high value of this infected part is highlighted with the cumulative heat map and the simple heat map. These are the results with the dataset 1. And for better understanding, we can say that here is highlighted the part, and this is with the second data set of action images. And whatever we have presented here is the summary. The important thing is we have this ensemble model with the soft voting system, with soft voting method, and covering it all. Yes, we have this few future works can be implemented and can be implemented for the research for our MS and PhD students as well, where many extensions can have to work on it in a better way. And like we can have different ensemble methods like stacking and bagging. Cross validation using deep neural network could be employed in research work. And while the current work focuses on COVID-19 infection, yes, we can see around us, even after COVID-19, many other diseases are erupted, but in small areas. And we wish and pray that this world is saved from any such calamity that is faced during the time of a peak time of COVID-19. And thank you for the listening. And here is the published work of what is presented here with some addition of stuff, giving the brief overview and introduction and the understanding of this idea of explainable artificial intelligence. Anyone can easily download this article, read it out, and if you have any question regarding this presentation, regarding this talk, regarding this article, the authors, and all the authors are available, especially the presenter myself is available. You can contact me on the email. My WhatsApp, email, WeChat is also available. The given number is here on the screen. Thank you again for the listening, and especially for the university for inviting me. It's all from my side. Any question, please?
Thank you, Dr. Jabbar, for your presentation. Students, please, you can ask the questions now. Thank you, Dr. Jabbar. It was a very interesting speech. I have one question from my side.
Yes, please.
Is this approach currently is deemed only as a theoretical matter, or is already some way implemented in industry?
Obviously, this explainable AI, if we talk about the explainable AI, this explainable AI is not new. It's more than 3 to 4 years, and this explainable AI is is one of the hot topic. And if we look and search on the internet, particularly the research databases, we can find that even the articles and this explainable AI is at its initial stages. And some researchers have already implemented it in their labs, in their various areas, in their researches. But coming to the single point of your question, this is in its infant stage, and a lot of challenges and many aspects are still explored for getting more and more out of this.
Okay, thank you. We wish you luck with combating COVID-19.
Thanks a lot.
Thank you, Dr. Jabbar. So now we are closing your part, and we will welcome the next presenter.